Welcome, my friends! In this video, we will discuss how to apply the central limit theorem to answer probability questions using a standard normal table. Make sure to check out my video on the central limit theorem first if you haven't watched it already. Also, I only intend students to either watch this video or the video about calculating normal probabilities using a TI-84 calculator, so if you watch both videos, there will be some repeated information. As a reminder, the central limit theorem states that for any probability distribution, the sampling distribution of the sample mean, x bar, will have a distribution that approaches the normal distribution as the sample size n increases. X bar will have an approximately normal distribution with the same mean as the original distribution and a standard deviation equal to the original standard deviation sigma divided by the square root of the sample size n. If the original distribution looks like this, or any other non-normal distribution, the distribution of the sample mean will look like this, a normal distribution, assuming the sample size is at least 30. Suppose the weight of adult males in a population is known to follow a normal distribution with a mean of 200 pounds and a standard deviation of 25 pounds. If we let x equal the weight of an adult male in pounds, then x is normally distributed with a mean of 200 and a standard deviation of 25. Let's say a sample of 16 adult males is taken. What is the distribution of the sample mean weight of 16 randomly selected adult males from this population? Well, if we let x bar represent the mean weight for a sample of 16 adult males, and we remember that the mean of the sampling distribution is the same as the mean of the initial distribution, and the standard deviation of the sampling distribution is the standard deviation of the initial distribution divided by the square root of n, we know that x bar is normally distributed with a mean of 200 and a standard deviation of not 25, but 25 divided by the square root of n, which is the square root of 16, and simplifies to 6.25. I often put a subscript x bar on the standard deviation of the x bar distribution, just to make it really clear which standard deviation I'm referring to. It's a bit redundant in this context, as it clearly applies to x bar, so it isn't strictly necessary, but it isn't a bad idea to include it anyway. I often don't put the subscript x bar on the mean mu, as it is the same regardless if we are referring to the initial distribution or the sampling distribution. Now hold on a minute, Luke, you might say. Doesn't the sample size need to be at least 30 to say anything about the sampling distribution? Our sample size was only 16. Great question. As the distribution of x is normal, the distribution of x bar will also be normal, even for sample sizes less than 30. Now, let's answer a few questions. What is the probability that a randomly selected adult male from this population weighs less than 180 pounds? Since we are asked about a single observation, we turn to the distribution of x and not the distribution of x bar. The probability statement is the probability x is less than 180. On the graph, we need to find the area on the curve less than 180, which I've shaded in red. To do this, we convert x equals 180 into a z-score using the z-score formula, x minus mu divided by sigma. This becomes 180 minus 200 divided by 25, which equals negative 0.8. Our new probability statement becomes the probability z is less than negative 0.8. X bar has been transformed into a z-score on the standard normal distribution. If we find the probability that z is less than negative 0.8, it will be the same as the probability x is less than 180. We can also add a second horizontal axis to the graph to put the z-scores. Remember that the mean has a z-score of 0 since it is 0 standard deviations from the mean. Let's look for our z-score in the table. The table I'm using gives the probability from the center of the distribution up to the z-score. There are no negative values in the table, but since the normal distribution is symmetrical, we can search for positive 0.8 and still find the correct probability. We see here that the probability associated with a z-score of 0.8 is 0.2881. 0.2881 is in this area of the graph, but of course we want the area in the tail of the distribution, which I've shaded in red. We take 0.5, which is the area of everything to the left of the center of the distribution, and subtract 0.2881 to find the tail area, which is 0.2119. There is about a 21.19% chance of a randomly selected adult male from this population weighing less than 180 pounds. What about the probability that the mean weight from a random sample of 16 males is less than 180 pounds? This is the probability that x bar is less than 180. The graph looks the same as it did in the single observation case, except now the horizontal axis is x bar instead of x. Do you think this area is larger or smaller than the probability we found based on the single observation case? Let's find out. First, let's convert x bar equals 180 into a z-score. The z-score calculation is essentially the same as it was in the single observation case, except now we have x bar instead of x in the numerator, and the denominator has the standard deviation of x bar, which we know to be 6.25. We have 180 minus 200 divided by 6.25, which is equal to negative 3.2. The probability statement becomes the probability z is less than negative 3.2. We can also add the second horizontal axis to the graph to put on the z-scores. Let's find 3.2 in the table. Here is the table again. Remember that we need to take the positive z-score, so the probability associated with positive 3.2 is 0.4993. The area from the table is the area from the mean down to our z-score, which does not correspond to the shaded area since we need the tail. To find the tail area, we take 0.5 and subtract 0.4993 to get 0.0007. Note that this distribution is not drawn to scale. The shaded area should be very tiny. There is a 0.07% chance that the mean weight from a sample of 16 adult males is less than 180 pounds. Wow, that's quite a bit smaller than the probability of 21.19% when we only considered one adult male. The reason the probabilities are so different is because averaging inherently reduces the spread of the data. That's why the standard deviation of x bar is so much smaller than the standard deviation of x. It's fairly likely to sample one individual and find a value very far away from the population mean, but if you are sampling several individuals and averaging those observations, large deviations from the population mean become much rarer. Let's look at another example. Suppose the number of steps Walter takes in a day is uniformly distributed from 2 to 5,000 steps. What is the probability that Walter walks between 3,700 and 4,000 steps on average in 36 randomly selected days? Notice that the distribution of steps is uniformly distributed, and we aren't given the mean or standard deviation. If you are familiar with the uniform distribution, you know that there are simple formulas for the mean and standard deviation. You can check out my video on the uniform distribution for a more complete explanation. If we let x represent the number of steps Walter takes in a day, then x follows a uniform distribution from 2 to 5,000. The mean is a plus b divided by 2, which is 2,000 plus 5,000 divided by 2, or 3,500. And the standard deviation is the square root of b minus a squared divided by 12, which becomes the square root of 5,000 minus 2,000 squared divided by 12, which simplifies to about 866.03. Since n is 36, which is greater than 30, we can use the central limit theorem. We let x bar represent the mean number of steps Walter takes from a random sample of 36 days. X bar follows a normal distribution by the central limit theorem, with a mean of 3,500 and a standard deviation of 866.03 divided by the square root of 36, which simplifies to about 144.34. We want the probability Walter walks between 3,700 and 4,000 steps on average from a sample of 36 days. The original distribution is uniform, but that is irrelevant for this problem since we are dealing with the sampling distribution of x bar. The sampling distribution of x bar is normal, and the desired area is shaded in green, which is between 3,700 and 4,000. The probability statement is the probability 3,700 is less than x bar is less than 4,000. To answer this question, we need to convert 3,700 and 4,000 into z-scores using the formula. The z-score for 3,700 is about 1.39, and the z-score for 4,000 is about 3.46. The new probability statement in terms of z-scores is the probability 1.39 is less than z is less than 3.46, which is equivalent to our other probability statement. We can add our second axis to include z-scores on our graph. Let's look for the z-values in the table. We see that the probability associated with a z-score of 1.39 is 0.4177, and the probability associated with a z-score of 3.46 is over here at 0.4997. Back with our distribution, the area from the middle up to z equals 1.39 is 0.4177, but that's not the area we want to solve for. The area from the middle up to z equals 3.46 is equal to 0.4997, which is made up of two different sections of the graph. This also isn't the area that we need. 0.4997 covers the correct area, but it also covers a portion of the curve that we don't want, specifically the white area, which equals 0.4177. So we take 0.4997 and subtract 0.4177 to get 0.082, or 8.2%. Again, the distribution is not drawn to scale. It's simply there as a guide to help us visualize the probabilities. There is an 8.2% chance that Walter walks between 3,700 and 4,000 steps on average on any random 36 days. How about this question? What is the 30th percentile of average steps that Walter takes from a sample of 36 days? Well, let's start with a picture. We want some value for steps such that 30% of sample means fall below that value. A percentile always tells you the percent of observations below that value. The 50% area to the left of the mean can be split up into two parts, one below our value of x bar, which is 30%, and one between our value for x bar and the center of the distribution, which is 20%. The table gives us the area from the mean up to some z-score, or down to some z-score if it's negative, so we need to search for 20%, or 0.2, in the f of z column of the table. We know to look in the f of z column because 0.2 is a probability and not a z-score. Here we are with the table. We are now working backwards. We have 0.2 as the area, or f of z, so we search for 0.2 in the right-hand column. The closest value is 0.1985, which corresponds to a z-score of 0.52. Different teachers might have different conventions for what to do when the value does not fall exactly in the table, but I'm fine using the closest value, which is 0.52. The value we got for the z-score is 0.52 from the table, but we will use negative 0.52 because our desired value for x bar falls below the mean, suggesting a negative z-score. We can include the second horizontal axis on the graph to include the z-score. Now we need to convert this z-score into a value for x bar so that the units are in steps instead of standard deviations. Recall the formula to find the raw score, which is x equals z times sigma plus mu. If we want to solve for x bar instead of x, the formula is the same, except for we have to use the standard deviation of x bar instead of the standard deviation of the initial distribution. So we have x bar equals negative 0.52 times 144.34 plus 3,500, which is equal to approximately 3,424.94. We can include this value on the chart, rounding to 3,425 to save space. The 30th percentile for an average of 36 days of steps from Walter is 3,424.94. Meaning that on any sample of size 36, the average number of steps that Walter will take will be below 3,424.94 30% of the time. Alright, that wraps up our examples using the central limit theorem to solve for probabilities using a table. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.